Welcome to my thesis defense. Today, we're going to talk about probabilistic modeling of air and ground vehicle trajectories. Many traffic-related systems, including aircraft collision avoidance and autonomous driving, are required to go through in-depth risk assessment in order to comply with the strict safety standards. For these safety-critical systems, validation in the real world can be expensive and hazardous. Instead, validation through simulations are widely used as they allow us to test a wide spectrum of scenarios without the risk of death or injury. To build effective simulations, it is important to have trajectory models that are representative of actual human behavior. There are several approaches to model vehicle trajectories. Rule-based models assume that the driver or aircraft behavior is governed by predefined equations with a limited number of parameters. One example is the intelligent driver model. Data-driven models do not have explicit governing equations, but they learn the driver or aircraft behavior directly from data. As examples, we have recurrent neural network and GMN, Gaussian mixture model. For emerging domains with limited data availability, we can leverage expert knowledge for building trajectory models. One approach is to learn experts' behavior from demonstrations as done in preference-based learning. Another one is to have experts build models using an assistive software interface, such as Genie. Modeling vehicle trajectories is challenging due to various reasons specific to application domains. For the autonomous driving domain, trajectory models need to capture the inherent uncertainty in human behavior and the complex interactions among drivers. We want a model that learns the above from data, but at the same time, we want the model to be interpretable. For the conventional types of aircraft, trajectories are heavily reliant on the structural information represented by the flight procedures and the instructions from the air traffic controllers. However, in dense airspace, aircraft behavior may vary according to preferences of the controllers and the correlations among multiple aircraft. We need a model that captures both the patterns and the variability in aircraft behavior. For new types of aircraft, such as urban air mobility, the major challenge is the lack of available data to build models upon. There are three main contributions of my research that address the challenges in each domain. The first contribution is modeling human driver behavior. I used a hybrid driver model by combining rule-based models and data-driven learning approach. The second contribution is modeling aircraft behavior along with structural information. I used a generative approach that incorporates varying aircraft behavior over multiple flight stages and captures pairwise correlations among multiple aircraft. The last contribution is modeling aircraft behavior during close encounters using expert knowledge. I will introduce a software package called CONTRAIL that provides an interactive modeling framework for building aircraft encounter models. Let's begin with the first contribution. For the successful integration of autonomous vehicles into existing roadways, modeling human driver behavior plays an important role. Recently, data-driven models have gained attention. They are also called black box models because they have zero knowledge on the underlying logic or the internal structure. while being highly expressive, meaning that they can learn the complex behavior from data. These models are less interpretable. On the other side of the spectrum is the rule-based models, or white box models, as they have full knowledge. While being more interpretable and simple, which makes it easier to prevent unacceptable behavior, these models cannot model the inherent stochasticity in human behavior. To leverage the advantages of both models, I proposed a hybrid model which estimates the parameters of rule-based models using data. Recent studies that use a hybrid model includes Bhattacharya et al. To 2020 and 2021. Both works intended to model driver behavior on a single lane scenario and use the IDM, a car following rule-based model. Then they estimated the parameters of this model using particle filtering algorithm. My work has extended these works to a multiple lane scenario. I proposed a model that constructs a probabilistic latent variable model by combining two deterministic rule-based models, a car following model and a lane changing model. Then I used the expectation maximization, or EM algorithm, for the parameter estimation. There are some advantages of using the EM algorithm. First, we can use expert knowledge to define the prior distributions over the parameters. Second, the algorithm monotonically increases the likelihood with each iteration. So we can have higher data efficiency. For the rule-based driver models, I used the stochastic IDM and mobile. The IDM is a car-following model that governs the longitudinal acceleration along the lane, which aims to drive the vehicle at its desired speed while maintaining the safe separation from the front vehicle. The stochastic IDM encodes some stochasticity by adding a variance term to the standard IDM. The mobile is a lane-changing model that governs the lateral motion. It computes the longitudinal accelerations of the ego vehicle and its neighbors, defined as the old follower and the new follower. For both cases, when the ego vehicle has and has not changed lanes. Then, if the weighted sum of the accelerations for the lane-changing case is greater than the other case, and if that difference is greater than some threshold value, a threshold, the model initiates a lane change. Now, I'll explain how to construct a probabilistic latent variable model by combining the IDM and mobile, and how to learn the distributions over a subset of the parameters of these models. In this work, X denotes a set of known variables consisting of the longitudinal and lateral position measurements of each vehicle. Then Z denotes a set of latent variables, including the desired speed parameter from the IDM, the variance term from the stochastic IDM, the politeness parameter from the mobile, and the lane changing parameter lambda, which will be discussed in the next slide. We assume these are multinomial variables, and the goal is to infer Z by observing X. Assuming the latent variables are given, we can compute the probability of a vehicle changing lane at each time step, denoted by F lane. In this page, I omitted the notations for the time steps. I used a sigmoid function to replace the hard constraint of mobile into a soft one. This incorporates stochasticity of the lane changing behavior into our model. Here, lambda is the parameter that governs the degree of preference for lane changes. Then the empirical likelihood of the next observation, x dash, is obtained by the sum of the likelihoods in the lane changing case and the lane following case, weighted by the probability of each case. The likelihoods p change and p follow compute the probability density of the true next position x dash, given the predicted next position derived from the current positions x and the latent variables z. Our goal is to find theta, or the governing parameters of z, that maximizes the empirical log likelihood of all observations. Since the log likelihood function contains a summation inside a logarithm, we can't find an analytical solution for theta. Instead, we can construct a tractable lower bound of theta, or lower bound of the log likelihood that contains a summation of logarithms, and then use the EM algorithm to find theta to maximize this lower bound. The EM algorithm iterates E step and M step until convergence. In the E step, we compute the posterior probabilities of Z given X and theta. In the M step, we compute the maximum likelihood estimates for theta using the updated posterior probabilities in the E step. I experimented the model on a highway driving scenario with lane changes from a real-world data set called Interaction. Two baseline models were used to compare our model against. The first model uses the default IDM and mobile parameter values suggested in prior work. The second model uses particle filtering to estimate the IDM and mobile parameters. I evaluated the models in terms of three metrics: prediction accuracy, data efficiency, and safety. The prediction accuracy is measured using the average displacement error and the final displacement error between the simulated and the ground truth trajectories. The table shows the ADE and FDE of each model for 5-second duration and 10-second duration. Results show that the EM model outperforms the default model and has nearly equivalent performance to the particle filtering method. Next, the data efficiency is evaluated by training the models using subsets of the data set with different sizes, and then measuring the average displacement error for 5-second duration. We can observe that using the small data set, both particle filtering and EM models perform as poorly as the default model. Using the medium data set, the performance of the EM improved more than the particle filtering model, indicating that the EM is more data efficient. Finally, the safety is evaluated by counting the frequency of collisions in the simulated trajectories. If a vehicle is following its lane, collisions are counted when the headway distance is smaller than the vehicle length. During a lane changing period, collisions are counted when the L2 distance to another vehicle is smaller than 0.5 meters. We can observe that the EM achieves almost half the collision rate of the particle filtering. Here, the default model does not produce any collisions, as the IDM and mobile are designed to be collision-free. However, it suffers from poor prediction accuracy, as we saw in the previous results.
So what's the frequency? What are the units on that?
Oh, that's the the number of collisions over the pair of trajectories, or the number of vehicle is the denominator. And then I only counted once if a vehicle has a collision with another vehicle or not.
Okay,
Did that answer your question?
yes.
Okay. Yeah, so from the three different results, we can conclude that the EM outperforms the default model and is comparable to the particle filtering with higher data efficiency and safety. Now let's move on to the second contribution. For the aircraft flying under instrument flight rules, trajectories depend on a series of standard flight procedures and instructions from air traffic controllers. For example, an arrival aircraft entering the terminal airspace from an air route follows a standard terminal arrival route, or STAR. Then when it gets close enough to the destination airport, it follows the instrument approach procedure, or IAP, for the final approach before landing. For a smooth transition from STAR to IAP, the air traffic controllers guide the aircraft by assigning specific headings, and this is called the radar vectoring operation. Although the aircraft behavior is heavily reliant on the procedures and instructions from controllers, it may vary according to the preference of the controllers and the correlations among multiple aircraft. Also, the aircraft behavior differs among their flight stages in terms of variability in their positions with respect to their procedures. For example, aircraft in their departure and approach stages tend to vary more in their positions than in the other flight stages. Here are some prior work that are closely related to my research. Gariel et al. Tried to find the nominal patterns of trajectories in a broader control area by computing the turning rates and then clustering the turning points. Malbovi and Kukenderfer used a Bayesian inference approach to learn the transition distributions between the turning rates of trajectories around small airports. Barat et al. Used a Gaussian mixture model to learn the position measurements of trajectories in the final approach and the initial climb stages. All these models do not incorporate the procedural information. The objective of my work is to build a model that can first learn the aircraft behavior in relation to flight procedures from data without having to hard code the aircraft dynamics. Second, incorporate varying aircraft behavior among flight stages. Third, incorporate the pairwise correlations among multiple aircraft. And finally, generate realistic trajectory distributions given new flight procedures. In this work, two kinds of data are involved. First, we have the trajectory radar data. I used arrival flight tracks to John F. Kennedy Airport, and the scope is 30 nautical miles from the airport. I converted the data so that each entry consists of time, track ID, and the local east-north up positions. The figure shows a 2D histogram of the arrival tracks to all runways of JFK. We also have the procedural data. For the arrivals to JFK, the range of 30 nautical miles covers the radar vector and the final approach stages, but not the initial approach stage. So the stars were not used in this work. For the vectoring stage, we don't have published standard procedures. Therefore, I extracted the nominal path from the actual trajectories and used them as the given procedures. For the final approach stage, I used the published IAPs. The figures show the arrival trajectories and the procedures for JFK runway 04 right. We can see that there are different radar vector procedures depending on where the aircrafts are coming from. Then they merge into a single IAP. Using the data, the goal is to learn a Gaussian mixture model of the deviations of aircraft trajectories from the procedures for each flight stage. As the input for the Gaussian mixture model for each flight stage, we need a pair of aircraft trajectory dataset and procedure dataset. And so I pre-processed each trajectory data by first partitioning it into the radar vector and final approach segments based on the distance to IAP, and then labeling it with a radar vector procedure using dynamic time warping method. The dynamic time warping can measure the similarity between two sequences with different length using a dynamic programming approach. One more thing we need to consider is that the input vectors of Gaussian mixture model should be in the same size, while the actual aircraft trajectories are in different lengths. In this case, we can use an interpolation method. I used the piecewise cubic Hermite interpolation method, the idea of which is to fit a function piecewisely using lower order cubic polynomials. After all the pre-processing is done, we have an input data set for each segment, which consists of the interpolated aircraft trajectories and procedures of all runways. The input vector of our GMM consists of the transit time, total distance, and the difference in the ENU positions of the aircraft and the procedure. For each segment, a GMM is trained to find the maximum likelihood estimates of the parameters pi, mu, sigma for each Gaussian component. The input data of GMM, and therefore the covariance matrices of each Gaussian component, is very high dimensional. To reduce the noise and possibility of overfitting, I performed an eigen decomposition of the covariance matrices and approximated them with the k largest eigenvalues and corresponding eigenvectors. To determine the optimal rank k, I used the probabilistic principal component analysis, or PPCA. The PPCA assumes that the input x is generated by having a lower dimensional latent variable z, and then mapping it into a higher dimensional space. Using different numbers of principal components or dimension k, we maximize the likelihood P of x by finding the maximum likelihood estimates of the parameters W, mu, and sigma. And the goal is to find k that achieves the highest likelihood. After we train the GMM with the rank k approximation, we can generate a synthetic trajectory given a new set of procedures in the following steps. First, we can generate the radar vector segment of trajectory by selecting one radar vector procedure and then sampling a sequence of deviation from the trained GMM. And finally, reconstructing the trajectory of aircraft positions. Then we can generate the final approach segment of the trajectory by first sampling a sequence of deviations by conditioning on the first n deviations computed with the last n points of the radar vector segment. Then by reconstructing the trajectory of aircraft positions. Now, I'll explain how the single trajectory model can be extended to a multiple trajectory setting using a pairwise modeling approach. For each combination of procedures, we train a pairwise Gaussian mixture model whose input tau pair includes the deviation trajectories of two successive aircraft and the inner arrival time between them. To generate multiple trajectories, we first construct a mean vector and covariance matrix using the pairwise model to sample tau set. Then we reconstruct the aircraft position trajectories in the same manner as in the single trajectory model. In the next slide, I will elaborate on how to construct the covariance matrix of tau set for 3 trajectories. It starts with constructing sigma 1 and 2 subcovariance by sampling a Gaussian component from the trained pairwise model. So we have populated the elements of the covariance matrix that corresponds to the pair of the first and second trajectories. Then we construct sigma 2 and 3 subcovariance by choosing a Gaussian component that has the closest sigma 2 subcovariance to the sampled one in step 1. Now we have populated the elements corresponding to the pair of first and second trajectories, as well as the pair of second and third trajectories. Finally, we construct sigma 1 and 3 subcovariance by choosing a Gaussian component that has the closest sigma 1, 1 and sigma 3, 3 subcovariance matrices to the sampled ones in step 1 and step 2. So this way we can construct the covariance matrix for the 3 trajectories. I experimented the models on JFK arrival data. Data for runway 13 left was used for validation, and the rest was used for training. To determine the optimal number of components in GMMs, I used the silhouette score. This score measures how close a data point is to its own cluster compared to the neighboring cluster. We had the highest score with 2 Gaussian components for the final approach model and 6 components for the radar vector model. Then the PPCA was used to determine the optimal rank for the low rank approximation. With the empirical data, we found the number of principal components or the dimension of latent space that maximizes the marginal likelihood. For a quantitative analysis, we tested both models on multiple trajectory scenarios. We used the Jensen-Shannon divergence score, which is a symmetric bounded form of KL divergence. The graphs show the empirical distributions of the XY position coordinates, horizontal speed, and distance to the closest aircraft for the actual data set and 2 synthetic data sets generated from each model. From the 3rd and 4th graphs, we can observe that the distributions of the multiple trajectory model is more concentrated near the mode than those of the single trajectory model. This result is probable because the multiple model learns the pairwise relations between aircraft, and so individual trajectory has smaller degree of freedom. In terms of JS divergence, the multiple model outperforms the single model for the horizontal speed. For the closest distance, the single model has a slightly better score. However, what's more important is the loss of horizontal separation, which is defined as 3 nautical miles, occurred more often in the trajectories of the single model. These results indicate that the multiple trajectory model performs better, or at least comparably, than the single model in terms of both similarity and safety. For a qualitative analysis, I plotted both the actual and the generated trajectories to JFK 1-3 left with the procedures. We can observe that the model can learn the general behavior of aircraft with respect to the procedure, but not the distinctive patterns of each individual procedure. This is because our model was trained on an aggregated data set for all different procedures and runways. We also generated 3 trajectories using the multiple trajectory model. Here, each figure consists of a top view and side views. In case 1, we can observe that the orange aircraft gets close to the blue one, then it detours its way and decreases speed until it has enough separation. However, in case 2, the orange and green aircraft do not satisfy the horizontal separation criteria. This undesirable scenario may have been caused by the intersecting procedures of the 2 aircraft. The last contribution is the aircraft encounter modeling framework called CONTRAIL. As new types of aircraft are emerging, we also need new trajectory models that can represent their operational environment. The urban air mobility, or UAM vehicles, are one of the main emerging types of aircraft that are intended to deliver small packages or passengers at lower altitudes in urban areas. As these vehicles will be operated above urban area, a collision may cause hazardous situations. Moreover, as the UAM operations increase, they are likely to be in high risk of collision. Therefore, for the UAM vehicles, it is particularly important to build aircraft encounter models, which are the statistical representation of typical aircraft behavior during close encounters with other aircraft. Since we have limited data availability of UAM trajectories, we can instead leverage expert knowledge to build encounter models. One approach is to learn experts' behavior from demonstrations. Katz et al. Used preference-based learning to learn the experts' preferences over encounter models through pairwise queries. Another approach is to have experts build models using assistive software interfaces. Genie is a development environment for building graphical decision theoretic models, such as Bayesian network. We take the second approach. So CONTRAIL is a software interface that supports field experts in building aircraft encounter models. This tool is developed using Dash, a Python framework for building web applications with interactive data visualization. Using CONTRAIL, the modelers can load and save files, visualize the encounters and modify them, build encounter models, and go through an iterative process of getting feedback from the tool and improving the model. This is a snapshot of CONTRAIL running on a web browser. Once a waypoint file is loaded, we can select a single encounter ID and multiple aircraft IDs from the drop-down menus. Then the selected trajectories are visualized in multiple aspects. On the left side, we have a map and data table. The trajectories are visualized on the map, which is by default centered to the reference point. Then the table shows the positions, velocities, headings, and turn rates of each waypoint. For the positions, we can see both the geodetic and the local east-north of coordinates. On the right, we have graphs that visualize key takeaways. In the first row, we can see the 2D graphs of XY positions, horizontal distance between the aircraft over time, and the horizontal velocities over time. In the second row, we have the altitude, vertical distance, and vertical velocities over time. Using the slider bar on the right, we can move through the timestamps to see how all of the values progress over time and whether the aircrafts are in the risk of collision. In the other tab, we have a 3D graph of the trajectories. This allows us to monitor the risk of collision more intuitively. In CONTRAIL, we can build an encounter model as a multivariate Gaussian distribution. We first need to specify the nominal encounter path by either selecting an encounter set from a loaded waypoint file, which was explained in the previous slide, or by directly constructing them in the create mode. So in the create mode, we can generate a nominal trajectory by setting the time intervals and altitude values and clicking a series of waypoints on the map. We can also drag the tooltips to fine-tune the trajectory. You can see that the position values of each waypoints are updated in the table. During the process, we can always update the heading, turn rate, and speeds in the table by clicking the update turn rate or speeds button. We can verify whether the values are reasonable, and if they're not, we can change the coordinates to fix this by dragging the tooltips in the map or by making direct changes to the table. For example, this new waypoint results in a turn rate greater than 5 degrees per second. This is not desirable, as the standard turn rate is defined as 3 degrees per second. So we change the coordinates to have the desirable value for the turn rate. Once the nominal encounter trajectories are specified, we can construct a mean vector, which is the flattened version of the 3D nominal trajectory with n waypoints, and a covariance matrix where each element is a function of 2 elements of the mean vector in the same order. We have 2 options of covariance type, and each type defines the function k differently. For both types, the horizontal elements have no correlations with the vertical elements. The difference is that for the diagonal covariance, all horizontal elements share the same value, and all vertical elements also share the same value. On the other hand, for the exponential kernel covariance, each element can take different values because it is computed by the difference between its 2 input values. In a pop-up window, we can specify the mean and covariance of the Gaussian distribution, as well as the number of encounters to sample. Then, once the generation is complete, CONTRAIL outputs histograms of the generated data. Looking at the output, experts can get feedback on the effects of the probability distributions on the paths and improve the model using their domain knowledge and feedback from the tool. To summarize my contribution, first, I presented a hybrid rule-based and data-driven driver model to achieve both expressivity and interpretability. I constructed a probabilistic latent variable model by combining two deterministic rule-based models. Then, EM algorithm was used to estimate the parameters of the underlying rule-based models. Second, I presented a generative approach to model aircraft behavior with structural information in terminal airspace. The GMM was used to learn the relative positions of aircraft and procedures of each flight stage, and to generate aircraft trajectories given new procedures. Then I introduced an extended model that can capture the pairwise correlations and generate multiple aircraft trajectories. Finally, I presented an interactive modeling framework, CONTRAIL, which supports field experts in building aircraft encounter models when they have limited data availability. Using this interactive tool and its user-friendly interface, modelers can iteratively build models based on their domain knowledge and constant feedback from the tool. Here are some potential directions for future study. For the driver modeling domain, we can explore other probability distributions for the parameters of underlying rule-based models to better represent the actual human behavior. Also, we can analyze the generalizability of our model to more complex scenarios and other data sets. For the air traffic modeling domain, we can investigate how to generalize the trained model to traffic environments that have distinctively different characteristics than the training data. Also, I think we can further reduce the dimensionality and improve our model by using other definitions for the deviation of the aircraft from the procedure. Additionally, further investigation on the interactions among aircraft may lead to a more representative model. For the aircraft encounter modeling, we can include other options of statistical models, which will potentially better represent the aircraft behavior. Also, we can improve the interactive modeling process by including additional statistical analysis on the generated outputs and adding some comparative analysis on previous models. I will conclude with the acknowledgement. First, I want to thank Lincoln Lab, MIT Lincoln Lab, Airbus A3, Toyota Research Institute, and Virtual Vehicle for funding my research during my PhD years.